Hello, this will be the beginning of a potential series covering the science behind cameras and lenses, and how to apply that science in computer graphics. In this video, we will be modeling a fully 3D camera lens from real patent information. There is a reason behind doing this. We are trying to achieve an artistic effect that cannot be done with default depth of field or textured depth of field. Another YouTuber recently created a video covering this topic, Sir Andalot, where he simulated an entire camera. His results are very unique and have their own purpose. However, my task is to make something potentially usable in production. Let's get started. My first step, generally speaking, is finding a patent to use. So there are several places where you can find patent information. You can find them specifically attached to the lens that you're trying to model on this set of forms. So we have our website here that contains an extremely large list of patent information, which has more patent information here. So I'm going to look for a lens that I think would be pleasant to view. So let's see. A lot of the times you can see these F numbers. F1.8 is a relatively fast lens, F1.4 is very fast, and F4 would be very, very slow. And by lens speed, we are talking about the amount of depth of field that the camera has. In this example, we can see that this would be an extremely slow lens. The reason it's referred to as a slow lens is because the exposure time would take a very long time with such a small aperture. While in this image, we can see that the exposure would be very fast due to how large the aperture opening is. It's letting a lot more light through to the sensor itself. We are going to try to find a fast lens that hopefully doesn't have any aspherical elements. You see this blue element right here? That means that the element is aspherical. We do not want to mess with aspherical elements as of now. They are a mess to deal with, and I could cover that in a later video, but I don't think people care for that right now. We're gonna start looking for a patent now. This is the first step of our process, and I'm going to explain the intricacies of looking for specific information on these patents and what you want to look for. So, my current mindset with what I want in a lens is I want a very long lens, something very zoomed in, something very portrait-ish. That way we can get a very nice looking depth of field, a very nice background, while still having very crisp and clear detail. So this form that we're looking at right here is a list, a very large list of lens patents from all sorts of companies covering almost anything that you could imagine. There's another example over here that I was looking at, but this wasn't one that I wanted to copy. I'll explain to you what some of this information means though. Right here, we have an 85mm lens. That would be a portrait lens. It's fairly zoomed in, not super zoomed in. It's not nature photography zoomed in, but it is not wide angle by any means. 50mm would be a standard focal length. That would be something that you'd see in most cinema productions, or most cameras in general will have, by default, 50mm lenses. And then we have this little F number right here. This F number represents the aperture size of this lens. It's not directly proportional to the aperture size, but it is a general way of summarizing it. So, with an aperture of f1.4, that would be the maximum aperture size. That's the maximum amount of light that it lets through the lens to the sensor. This would be a very fast camera lens. It wouldn't be ultra fast, it would just be very fast. And the reason why I want to use a very fast lens like this is because it looks very good even if it's stopped down. And by stopping down, I mean closing the aperture ring. I mean, we are shrinking the opening that the light can go through to the sensor. If we had a lens with, for example, we'll actually go with f4. This lens has a significantly smaller aperture. this aperture opening is very, very, very short in a certain sense. And I can't really directly compare them because this one looks smaller by scale, but this lens is significantly larger in proportion. This one is a zoom lens as well, which is the reason why it has such a slow or small aperture in this scenario. And by aperture speed, I'm describing the pace at which it can expose light on a sensor. A fast lens would be a lens with a very large aperture opening, while a slow lens is a lens that has a very small aperture opening. Zoom lenses in general all have very, very small aperture openings. You can find some very fast zoom lenses, but they tend to be in the $8,000 range, not exactly something affordable, and they tend to have a lot of optics. So each semicircle here is an individual optic, and fast zoom lenses tend to have a lot of optics. I could find an example on this list here. This one's relatively fast. It's not super fast, but again, you can immediately see there's a lot more glass on this lens. To be quite frank, I'm very glad that this one proved my point so quickly. So this is why we're not going to be using zoom lenses. We're going to be using prime lenses, which are fixed focal length. They cannot zoom in, they cannot zoom out, they can only adjust the focal plane, which is all we need. So let's find us a lens that will work. Alright, I've found a patent that I'm happy with. This is a Canon 85mm f1.5 lens. f1.5 is pretty dang fast. Very large aperture opening, a lot of lights let through. This will create some very aesthetically pleasing bokeh or depth of field in the background, as it will have a lot of swirl and a lot of very pleasant characteristics to it. So we see this diagram right here. We see all these little lights, we see all these little lines and all this yada yada nonsense. Don't worry about it. What we're gonna do is we're gonna go to this website right here, and we're going to find the matching patent from the optical bench system. We have this right here, and we can find it through, I believe, this link? No. Oh, there it is. This is the link. So we have the optical bench. Don't worry about it. This website looks like it was written in 2006. It probably was, but it's an incredible source. It's an incredible tool. Absolutely impeccable. As we can see here, we zoom in. It is not a perfect focal point. That's completely fine. We don't need to worry about that. We can stop it down in case it looks very blurry in the future. So we can see here that there is a diagram in the background, while we have the actual diagram in the foreground. There is an explanation behind this. The patent this was pulled from was US 2645973 example 1, or the Canon Serenar 85mm f1.5. You can look up this patent, and 9 out of 10 times you will be able to find it. I could actually look for it right now. Alright, here we have the Google patent of this image. We can see here, there's the diagram, there's the lens. There are 2 examples. That's why this one was listed as example 1 and not example 2. Example 2 is a similar lens that serves a similar purpose, but it is not the same model. This one has an additional achromatic triplet, and this one only has an achromatic doublet right there. So we can find the official diagrams from these by going to the external links. This is eSpace, which is the best source that I've found for this information. We can go to the original document, and then we can find, if we go through the few pages that exist here, there it is. This is example 1. This looks like a wall of numbers. It looks like a whole lot of yada yada nonsense, bada bada boogie. Not what we need to worry about. Thankfully, All this information is incredibly useful for our purposes, which specifically what I'm looking at is this index of refraction number. This index of refraction number will be vital for us. Thankfully, our friends here at photons2photons.net have done a very large portion of the work for us, because the diagrams on these patents are oftentimes very, very inaccurate. They don't line up properly. As we can see here, the semicircles are not even close to lining up with our actual physically modeled diagram. What these guys did was they got this information from these patents, including, so this R number is the radius of each semicircle. We have our positive radiuses and we have our negative radiuses. A negative radius would represent a surface that is facing away from the sensor here. So we have the center of, so let's look at specifically this edge right here, right along here. This edge is facing away from the sensor, which is right here. That means that the center of this circle would be somewhere over here. Probably further out if I'm being completely honest, but that doesn't matter. Then we have these surfaces, which are facing towards the sensor. We have the center of this circle somewhere in this direction. This would be a positive surface, and this would be a negative surface. That is what these numbers represent. These are the radii of each of these surfaces, measured in millimeters usually, but they can vary depending on where or when the patent was written. So then we have this D number. This D number represents the distance between two surfaces. So we have D1 and D2. D1 right here is approximately 0.105 millimeters away from the first radius, which is this distance from here to here. That would be D1. We can see distance 2 is right here, which is this surface and this surface. These two distances are very different, and it is very obvious that we have the correct patent information here because distance 2 is 0.002 millimeters away from distance 1, which is accurate, judging by this diagram. So that is the information that we have regarding the actual surfaces themselves. Now we have the information of the index of refraction. That is this ND number. 9 out of 10 times, it will be just labeled as ND, but in some scenarios, it's not. You can gather what it is though, because you can use a range of numbers. The index of refraction doesn't tend to go below 1.05 or 1.45, my fault, and 1.9. Those are the general ranges that an index of refraction can go to. As we can see, these all lie in that range. Then we have our V number. This is the diffraction or dispersion number. We don't need to worry about this. It is very difficult to implement that, and we're not going to worry about it. So going back to this, we can simply take a screenshot of our diagram. If we want to, we can also zoom in over here. That way we get a higher resolution image that we can copy. So I'm going to bring this into Photoshop and I will implement it into Blender in a moment here. Alright, now we have Blender open. What I'm going to do is I'm going to import our image as a background. That way, actually, I believe this is the right one. No, this is not the right one. I would like to import it as a reference image. So I'm gonna go to my pictures. So I've imported my image successfully here. As you can tell, it's snapped to the camera's angle. That's not what we want. I'm going to just click Alt-R and reset its rotation. Now what I want to do is line up this blue line with the x-axis of the world's origin. That way it is centered perfectly in our image. So now we can go to our orthographic view, see if everything looks lined up properly. It does. Now, let's get started with tracing this diagram. What we need to do is create a circle that will be a representation, a 2D representation of every single one of these surfaces in these optics. So I'm going to go Shift A, Mesh, Circle. I would like to have 2048 vertices. It's divisible by 8, so it lines up with a lot of things that computers tend to do, and it's very, very high resolution. Very important that it is high resolution. And one final crucial detail is that if you go into edit mode, there is one vertice that lines up perfectly with the central axis of this circle. So what we're gonna do is, we're in edit mode right now, so we'll just go G, X, and line up the right or the left side of this circle with the origin of the mesh itself. Then what we're gonna do is go to the orthographic view on our camera, and make sure you're in wireframe view when you do this. If you go to solid view and box select things like this, there will be gaps in your selection. God knows why. So let's go to wireframe view and delete this half. This half will not be necessary for the construction of the lens. It will only be excess. It will have to be trimmed off later. So I'm going to delete it. And then we need to delete this half as well. This, again, will be excess. We will be trimming this off afterward, which is why we're getting rid of it now. So what we have here is our semicircle. This is going to be the building block of our lens, the first step in the construction of it. So I'm going to keep this off to the side here and make sure that I have an original version of this at like all times. Now let's duplicate it and line up the origin of it with the front of this surface right here. This is a positive surface, so the origin of our circle should be right around here. We are going to scale up this circle, which lines it up with this edge right along here. And then we're going to duplicate it. And we are going to trace this diagram as closely as possible. Thankfully, we don't have too many optics, so this won't take too long to do. So let's line this up with this curved surface. Whether or not the surface looks like a straight line, more often than not, it is curved. If the patent itself says that a surface is 100% straight, it will say that by giving you no radius. All of these surfaces have a radius though. This is the radius in millimeters. If we want to get extremely accurate details here, we can use these measurements to our advantage, but we don't need that level of precision. That, like I said, was already done by the guys at Photons 2 Photons. Or guy, whether or not it's run by one dude. So let's continue tracing these out. Now, there are these surfaces right here. If we scale this up, we will think, oh, we're done here. This is all we need to do. Not correct. We have two optics here. We have this optic and a sort of film between the two. There is no air gap between these two lenses. It is two different lenses. However, it is not one lens. There is two different indexes of refraction for these two lenses. We have this one and this one. That would be this lens and this lens, right here and right here. Now, how will we simulate this film between the two layers? We don't need to. All we have to do is duplicate this layer right here and move it over along the x-axis very, very, very little. Very little. Emphasis on very. So we can do this a couple of times for this one as well and for this surface as well. So now we have a negative surface. This negative surface, all I have to do is duplicate our semicircle, scale, x, -1, enter. And now we have a negative surface. Scale that up, line that up with this edge right along here, and then we duplicate it, gx, barely at all. Make sure you move it directly along the x-axis like this. You don't want to just eyeball it like this because that will mess up with the screw process in the later section. Now we have our aperture gap. This is a double Gauss lens design. So if we look at a double Gauss lens, if we look at a double Gauss lens, we will see that they all have a very similar pattern. It is very symmetrical looking design-wise in most of these. This would be a very good example of a symmetrical design, but they are not perfectly symmetrical. The perfectly symmetrical designs were completely outmoded after the decision from some of the Cook engineers in very, very late 1990s, I think, or early 1990s. I don't remember how long ago it was. History is not important. That's a joke. So we have the aperture gap right here. We just scale down our circle, line it up. This aperture gap we will take note of. We want to keep this size right here in mind. So we duplicate this. We have another negative surface, so sx -1. That sounded kind of funny. And then we line it up with this right here. We then go to here, and another quick little tip that you can implement. If you don't want to accidentally select your background empty and move this around, you can just click that. You can no longer select it now. So we duplicate this, scale it up. Since this is a doublet, this is an achromatic doublet, we need to do the same surface right there, like that. It can be arbitrarily distanced. It doesn't have to be super precise in that regard, but just make sure that they're very close. We duplicate this one more time. Actually, we're gonna do 2 more times. So we'll do that, and then we'll do that. And then we have one more surface to trace, which is right here. Scale it up, and boom. That is close enough. Now we have the block out of our lens. We have all of the surfaces modeled out. All we have to do now is flesh out the surfaces and optics themselves. So step 1 here will be to merge the surfaces. So we have optic 1, we have optic 2. I'm selecting on the left side of this, so it selects the object closer in proximity, which is the surface I want to merge it with. Control J. Select on the right side. Select on the left side. Right there. Control J. Select on the right side. And then we can just select this. Control J. I'm holding Shift, by the way, to select multiple objects at the same time. These are all individual now. And the next step of our process is to cut out the shapes. This is a fairly simple process, but it can get time consuming depending on the complexity of your model. So we'll just go Tab into edit mode, and we will click the closest lining up vertices to our diagram. You don't have to be super close with it. You don't have to be super precise. You can have excess. Excess is completely fine. So we merge these two together by selecting this vertice and this vertice, holding Shift, and then pressing F. Then what we do is delete these, tap L, L, X, delete. The reason we tap L while holding over the object is so it selects everything linked to it. You don't click while holding L, you just tap L over it. It selects all the linked objects, and you can even adjust what you want. That's not what we need to do right now. We have this one right here. We go here. We can actually line up this vertex with this vertex. Merge. Delete. L, L, X, delete. F. Right here, we want to keep this edge lined up right here, so we just go here, and then we go to here. That is good enough. So select, X, delete. L, L, X, delete. One more. So we can, since this is a box shape, we can either just go like this, which is the simplest way of doing this, or we can keep the original diagram in mind. So I will just extrude this vertex along the x-axis, and then merge it with this vertex right here. I would like to have a little bit of excess here in case something doesn't line up perfectly, so I'm going to go here, and then select here. The reason I'm selecting this edge is because I'm going to hide it, and then I'm going to select linked and delete these. And then I can just go Alt-H, and now we have our cleaned up edge. we now move on to the next optic. This one, as you can see, also has this. If you want to, if you're like picky and a little bit stingy with your modeling, what you can do is change your snapping mode from grid to vertex. That way we can go extrude y-axis. That way we're locked along that degree. And then you can angle it perfectly with this vertice right here by holding control. We then press F, select that, oopsies, select that, H, linked, X, delete, Alt H. Now we have that surface set up correctly, and then we can just do that with these next two ones. All right, we have our lenses set up properly. This is a two-dimensional diagram of our optical system. Now we don't need this anymore. So what we do next is the fun part in a certain sense. We are going to start refining the lens itself, or fleshing it out. So we're going to use a modifier called the screw modifier. This essentially spins a surface around its origin. What we want to align this on is the x-axis. That way we have our lens pointing in the correct direction. It's already starting to look like a lens, isn't it? So now we want to increase our steps to 256. That is a very reasonably high resolution, and it looks very normal. Now, this button right here on the screw shader or screw modifier is extremely important. Calculate order. This will set up the normals to where they are lined up correctly in the right direction. And then we go to here, normals, and hold Alt while doing this. That way the rest of the selected lenses here are all applied with the same effect. If we want to, we could even select this over here. Hold Alt and tap Auto Smooth. This doesn't look like it's making a difference right now, but it is applying this specific effect, or this specific factor or feature, I don't remember what it's called, to all of them. If I select this one, we can see it does have it applied. So now we just go back to our original setup over here. Control L, link modifiers, or copy modifiers. Now we have all of our lenses. This we don't need to worry about right now. We can get rid of that, it's gonna get in the way. We have all of our lenses now. Each of these has a correct surface, and they all are pointing in the right directions. Now we get started on the glass material. I'm going to use an HDRI so I can see the effects of the glass more clearly. I will be right back. All right, we're back. We have the HDRI selected. We can go to the render view now, and we can preview it. By the way, we want to be in the cycles rendering engine. This will not work with Eevee. We can disable the noise threshold. This will have negative effects on our render, and then we can disable the noise threshold in the render as well. Now let's get onto the glass material. So we select all of our circles here. We go to shader editor, new material, and then we delete this and add a refraction material. It is important that you use a refraction material and not glass, because glass will add a lot of unnecessary fireflies and distortions or like disturbances to the image itself. We have our refraction material now. We can go Control L, link materials, and that will copy all of these lenses to this one material. As you can see, there is a weird black splotch at the end of this. The reason we have this is because Blender's light paths don't generally compensate for this many refractive layers in front of one another. All you gotta do is set this to something like 28, and then set the transmission, or I believe it is. It's either that or transparent. Okay, yeah, it's transmission. You just set the transmission to something very high. Equaling the total is good enough, usually. Now, we can see this is not working as a lens. We are not seeing a focused image. We are seeing this warbly distorted looking mess. That is more or less to be expected at this stage. We are currently refining the optics still. This is where things start getting finicky. So if I isolate this lens right here, we can see it is focusing the light to a point. It is doing its job. That is what it needs to do. However, we can still see that in the middle of it, there's this little pin cushion, or this little pin right there. That will add a lot of distortion to the image in the future. That's actually a step that I missed. Hold Alt, that is how you apply everything to one of these, or from one to all of them. Hold Alt, click Merge. Hold Alt, edit this number, and set that to something unreasonably low. Now, if we isolate our lens again, we can see there is no more weird points in the middle of it. Perfect. Now, we're gonna go along these and see if the lens is doing what it needs to do. If we look at our diagram again, we can see here that we can measure which lenses are concave and which ones are convex, simply just using logic. I'm going to hide all of those. So this lens is convex. It is focusing light down. Convex, convex, concave. This one is concave because it has a negative surface here and a positive surface here. That makes the light focus further away from the point. It sort of spreads the light out. That's the best way to put it. Here's another concave lens that is iconic to a double Gauss design. Then we have convex, convex. So we can check to see if these lenses are doing what they need to do by isolating each one individually. It's tedious, but it's the best way to do it. This one is correct. Convex, focusing light down. This one is convex, focusing light down. Yep. This is a concave, and it is focusing light down, not what we want. We can tell it is focusing light down because it is focusing it to a point. This is where we select this one and enable flipped normals. That way, it is spreading out the light the way it's supposed to. This one will also have the same issue. We can see it is focusing the light down, not what we want. Flip normals. Then the rest of them should be a-okay. Yes. Now we're gonna look a little bit closer to the lens that we're thinking of. We can see that the light is coming to a focus, but it is not perfect. I can actually demonstrate that using some simple tricks. We're going to be making the sensor plate for the camera in a certain sense here. This is how we set up where the light focuses. So I'm going to duplicate this vertice right here, separate it from the original lens, and then extrude it out and extrude it back. This will create a very, very rudimentary, very basic lens shape. So we can make a new material here. Remove this material pass, add a new one, and then we can just delete the shader. No need for a shader, nothing to compute. It makes it much easier on your computer. Then we can just select our main circle right here again, and line it up with the back of our surface right here. So let's enable visible objects again, so we can scale it down, and then we can align this up with our vertice right here by just holding G, Y, and then holding Control, which is pretty convenient. So that lines up with the vertice right there. It's okay to have a little bit of excess, again, not perfectly precise, it doesn't have to be. And now we have all of our external light blocked off. There will still be weird artifacts along the edges here, and I will show what effects these cause. Those are essentially light leaks. They are not supposed to be there, and we don't want them to be there. Now let's add a camera. We're going to do a very, very specific setup with this camera, so take note. We are going to press Alt, R, RZ, 90 degrees, or actually, negative 90 degrees, and then we'll go RY, 90 degrees. We want the camera to be upside down here. The image projected from the camera lens itself will be inverted, as is demonstrated with real camera lenses, so we want our sensor plate here to be inverted. Now we move our camera lens, or camera sensor, right here, and set it to orthographic. Now, if we go to our camera POV, we can see we are looking through the back of the lens. However, we see a lot of excess around here, and this beige color is the HDRI itself. We reduce the orthographic scale, put it more or less lining up with our circle at the back of the lens. Now we enable depth of field. This is what makes our sensor plate a sensor plate. if we reduce the distance here, we can see we slowly but surely will get a more out of focus image. Now, I would like to line this up with our focal plate here, but we don't exactly have a focal plane. This will be about as close to a focal plane as we can get. Yeah, this right around here. Yeah, there you go. You can start seeing the image coming into focus. I'm going to make the back of our lens significantly larger. That way we don't have to worry about all this excess light at the edges. And then we can just extrude it back. Boom. We can see here, there's a lot of issues. It's not at all good looking. This is very distorted, very messy, but we can see an image here, which is pretty dang neat. This right here, by the way, is behaving as if it is a flat plane with caustics being casted onto it. The lens itself is is focusing the light down onto a plane, which is some arbitrary distance away from the origin point of the camera. Let's start refining the lens itself now. We have that index of refraction data from that patent that we yoinked earlier today. Let's get that information now. We have our eSpace website right here. This is the diagram that we have copied. So let us grab the information from it. First surface has an IOR of a 1.6 something. I'm guessing it's 6.2, yeah, 6.228. Press enter. Now, we move on to this next material. Duplicate this material slot. We do not want to override the previous material. We see the next one has 6.385 or 0.6385. Next one is 0.5163. That would be this surface. By the way, I'm determining this ignoring the image here. So we have this one, which we need to duplicate. Yes, I need to duplicate that. 5163. By the way, taking note, significant digits here are pretty important. They're not super important, but just keep in mind that it has 4 significant digits for a reason. So now we have 6889. We can already see here that we're starting to see some spherical aberration in the bokeh here, which is pretty neat. It actually looks pretty sick. Not an intended artifact, but this will be fixed as we increase and adjust these index of refractions. So now we have this one, make a new material slot, and then 5317. 5317. And then we go to here, new slot. 6584. Go to here, duplicate 6385. All right, our image here is completely blurry, but if we look through the lens here, we're starting to see it's focusing perfectly to a point. That is what we want to see. If we want to analyze the image even more clearly, we can change our interpolation mode from linear to closest. This gives us a pixelated grid for us to follow, and now we can see a very, very clearly focused image. Let us go back to our camera, and let us move our sensor and line it up with our diagram right here. Boom, we're getting a focused image. Isn't that sick? Ignoring this massive light leak across it, this is nearly flawless. The reason why I'm not lining it up perfectly with the sensor plate right here is because this right here is the distance of the sensor from the origin. It is 0.19, that's normally good enough of a distance. So, let us add our aperture. This will significantly reduce the amount of light leaks that we are getting. So I'm going to re-enable our circle 001 here. This was one of the main light blockers. So we can just duplicate this, line it up with our aperture from the y-axis. So we can see this little line right here is moving and it's lined up right there. We don't need this axis right here for the aperture. It is an aperture, so it's not necessary. Then we line up the vertex here. This is the interior circle of our aperture. And we are going to move it inward, GY, and line it up with our aperture. And that reduced almost, if not all, of the light leaks. Now we have a focused image. That's pretty dang cool, isn't it? We can actually focus this image even clearer by isolating a specific section of the render and then moving this around until we get a better focal plane or focal point. So I'm going to just focus it like that. Now we have our image. We can actually set up a sort of focus chart for this as well as that you can see that there is a circle of I can't remember the term, but we can see this vignette right here. This can be changed by adjusting the f-stops. Lower f-stops usually means a bigger circle. Doing this can actually reduce the aperture and reduce render times in some scenarios, which is very useful, but not what we want to do right now. So I'm going to lower this to something like 1, and then I'm going to increase our distance here. That way we get a brighter image. We move this back a little bit. We focus it up again, and then we can reduce our orthographic scale just a little bit. This is essentially controlling the sensor size. This is like a full frame sensor, for example. So now I want to set up a focus chart. I want to make this look very, very, very clearly focused. So let's make a new plane. Or actually, we'll go images as planes, and I'll be right back. We now have our plane. This plane right here is going to be our focusing chart. It is not where it needs to be right now, so I'm going to move it out and place it some arbitrary distance away from the camera. Generally speaking, you want it to be what would be around 20 feet. I'm going to scale this up a bunch, and we can see it is out of focus. And you want to know how to fix that? You move the camera back. This little camera right here, you move it back. That is essentially the equivalent of moving the lens forward. It's the same thing, just different parts moving. So we can line it up with our chart. And if we want this to be faster rendering, we can just delete that and make it a emission texture or shader. That should be good. But oh yeah, by the way, if you want to get this chart, I have a PSD that I will be providing in the description. So we can zoom in here. It's not focused at the edge or at the center here, but it is focused at the edges. That's a sign of Petzval distortion, which is where the focal plane is curved. It's very, very curved. This is cool. It adds a lot of artistic flair. We don't need to worry about that too much with this lens. If we want to fix it, we can. And I can demonstrate how, but it is a very, very tedious process. That is for another video. So I would like to focus this image, at least relatively. What we can do to focus it even better is stop down our aperture. Our aperture ring right here, all we got to do is duplicate it and scale it down. That way we preserve the original scale. And we can shrink it down to where... Okay, so now it's stopped down. Now we can move our camera around and we will have a much clearer focus on our image. So we're getting there. Boom. That should be good enough. By the way, the sensor, you can actually tell if an image is going to be out of focus or in focus by doing this. What I'm doing right now is I'm holding control and my middle mouse button. This makes it so that I can move the camera back and forth very precisely. We can see there is a bit of spherical aberration because it is not focusing to a perfect point. I could show what that looks like right here. Now, this is good enough by all means. It is well focused. It has a little bit of fuzziness. We want the fuzziness. It adds very pleasant artistic chives. Now we have our lens. We have our patent that we have copied, and it creates beautiful background bokeh. However, there are a couple of technical details that we need to discuss. Clamping is the first one. We do not want clamping. No clamping. If you clamp your light like this, it will dim your highlights, which will reduce the pleasantness of your render and potentially ruin it. We don't want clamping there. And what we also want to make sure is that this itself is not going to be in the way of anything important. So we can focus our image back on the HDRI. We can hide our chart, and then we can look to see what our bokeh looks like when it's out of focus. I would like to increase my sampling. For things like this, you can increase the samples to like 20,000 while you're testing, and it would be completely fine. It renders very quickly, even on like a mediocre GPU. Since it's only processing light. It's not processing any actual bounces. So we can see that our bokeh here is very, very pleasant to the eye. It's very even, very smooth. Doesn't have a lot of weird quirks or characteristics to it. At the edges, however, it does start getting a little wacky, which is the kind of thing that we're going for. Like, if I had a clearer focus, I would be able to show, but I don't. We can see that this has like a bright exterior edge and it's shaped very cone-like almost. That is an artifact of simulating the full lens here. Oopsies. And that is the point of doing this. Now I'm going to show how to implement this into a scene. I organized all of the objects here into a collection. We have everything I need, which is the sensor, all of the optics, and the light blocking planes. We don't need this lamp, we can get rid of it. We can get rid of this entire collection as a matter of fact. And then we can get rid of these empty circles here. I want to keep this one right here though, in case I want to modify this lens in the future. Let's just save it. There was a step I had forgot, which was to parent all of these objects to one object. That way, it's easier to transport them around. So set parent to object, keep transform. Now we can just move our camera around, and it's doing everything we needed to do. Also, ignore the random frame drops in my Blender. That's because my VRAM has pooed itself due to the crash. Here is a doodle that I had made a while ago. It's a pile of mossy rocks from Iceland, essentially. And the intention of this doodle was for testing depth of field. There are particles everywhere, there's tons of little sharp bits, reflective bits, and it overall is a very detailed scene. This scene, I already have a lens in it, which if we increase our exposure here, we'll be able to see more detail. They take quite a while to render, but the quality of it, once it does finish rendering, which again, it takes a while, but it will finish rendering, it looks super duper neat. I will show the finished product of this render right here. So with this scene, I had a different lens. I had a Mayer optic Gorlitz lens, and I can replace it with the lens we just modeled, but I would like to show what this one looks like first of all. As you can see, our camera is extremely far away from the main body of optics here. That is due to the fact that the main optics are significantly smaller than they were when I first modeled it. They are shrinked down so they fit into the scene proportion-wise, and this is what you end up looking at. So we can see the distance sensor from origin is around 0.14, which if we enable the limits, there we go, we can see that this is where our focal plane is, right there, boom, which is the correct distance it would be for a vintage lens like the Mayer Optics series. So we can disable that, and we can implement our lens that we just modeled directly into this scene, and I will show you how. So I would like to keep this camera angle. I like this camera angle a lot, so I'm going to Shift D, and then I believe Alt P clear parent and keep transformation. That way we have everything we want right where it needs to be. And then I'm going to delete this. Delete hierarchy. That's the wrong one. I believe this. Yes, it should. Delete hierarchy. Now we have an empty scene. We can go to this camera right here, Control 0. And if you're wondering why the exposure is so bright, that's because the lens itself can dim the scene significantly. Or brighten it, depending on how fast your lens is. But that's not super important at this moment. Let's just file, append. So we find our lens that we modeled, we go to the collection, and then we append the collection that we had just made. We do that, and now we have this massive block of black Muller. Just nonsense. This right here is, well, let me redo that. So we now have our appended camera. This rudimentary looking pile of cylinders and cones is our camera. We can move it around using the main body here, since we have all of these sections parented to this one piece right here. This makes it very easy to transport and very easy to manipulate. Now we have our original perspective, the original camera angle right here. This camera is upside down because there was already a lens attached to it, but most of the time you would not have the lens upside down, or camera upside down. I'm going to copy the location, copy the rotation. That way, it is aligned up with it. It is currently offset by 90 degrees. All we have to do is R, Z, Z, actually no, X, no, Y, Y. 90 degrees, negative, enter. And we can look at our orthographic camera right here. It is currently offset. It's not directly upside down. This is when we go R, Z, Z, or no, it's X, X. Sorry, I'm so brain dead. 90 degrees, enter. Now we can do a quick test with the lens being this big, because why the heck not? Sounds fun. Alright, we got our image here. It's very out of focus, very fuzzy looking. Not what we want, right? We want this to be in focus. What we can do is move the sensor, the camera here, by going G, Z, Z. And we can move it backwards. And we can adjust the focus. Moving it backwards moves the focus closer towards the camera, or closer towards the front of the lens here. So I'm gonna isolate this one little section right here, that way it renders faster. And then I'm going to reposition our camera until it begins coming into focus. You'll be able to tell because there will be a significant sharpening of information. Let's see if I can get it to finally focus. By the way, the reason why it's not focusing correctly right now is because this is not a macro lens, and we are focusing it at a very much macro distance. This will not work. I believe I cannot move the camera any further back without detrimental impact to the image. So I'm just going to scale it down, which is very simple. All I have to do is just go here and just scale this down. And we can start seeing our little circle here. I still can't remember the term. I'll have to figure that out later and caption this video with it. We see our little circle right here where the image is projected onto the camera. We reduced our orthographic scale, that way we can see more of our image. That's fine. A little bit of vignetting never hurt. So we move our camera lens, or camera sensor back until it starts coming into focus. We're starting to see it. There it is. It's coming into focus, and that is our focal plane right there. We can see our mossy rock friend, and we can see the beautiful background blur with this system. We can increase the orthographic scale if we want to increase the field of view a little bit. You can adjust that depending on your preference. I like keeping it pretty high because I like to see the vignetting near the edges here. Now let's let this render out for a moment and see what the background bokeh will look like with these settings. Alright, we have a clearer image now. we can see that there are these beautiful bokeh shapes on the left side here from the Petzval distortion I discussed earlier. And we can also see that there's a little bit of spherical aberration on this little piece right here. And there's a lot of astigmatism in the lens. We can see here that it is extremely blurry along this edge. That is due to the fact that we are currently far past where this lens is designed to focus with the size of our sensor here. It's pretty cool, it looks really cool, and it has a really neat artistic jive. This would be excessive for most renders, but for the sake of example, this looks very, very good. If we want to, we could use a better lens here. We could find another patent, but that would be something that you would decide to do. All right, one really neat effect that we can do with this lens is something called tilt shift. As an example, what you could do is place the camera lens on your sensor crooked, and that would offset the focal plane proportionally to where the camera lens is offset. So I've gone back to my original scene with my previous lens, which is a Mayer Optic Wurlitz. I don't know how to pronounce it, I'm not German. I completely butchered the name. Just looks like. Alright, so we have our scene, it's rendering out here. This one is... Honestly, I love the way this lens looks in this scene, but I'm going to show you what it looks like if I add some tilt shift. So we are going to select our sensor camera right in here. Let's see here, I need to go to wireframe view so I can actually see it. Should be right here. Yeah, there it is. So what we can do is just rotate it along the local x-axis, and that will offset the focal plane and sort of angle the way the focus is. I can I need to figure out a way to demonstrate this more clearly because this scene doesn't have a great example, but if I do this, we should be able to see it very clearly. Yes, we can see. So I think a better example would be if I rotated it vertically, because this scene already has a lot of depth of field. So if I do this, RYY, and then offset our lens and then shift it back over, we should be able to see what I'm talking about. Yeah, there we have it. You can see the focal plane here is extremely crooked. We can see that it's focused on the background here, on the foreground here, on the near foreground right here, and then the middle ground more or less right here, which looks really sick. It could be used to create some really neat abstract renders with a lot more depth than you would get with normal Photoshop tilt shift or with some cheap editing app. And doing this ends up creating a really unique aesthetic that is impossible to simulate with normal cameras. And I think that is really powerful. I will probably be posting these at least before this video is published, so you will be able to see them on my Instagram page. I'm going to follow this video up with another set of explanations and tutorials for some of the terminology behind camera lenses, but that will be if this video gets some good reception. Thank you guys for watching this, and have a wonderful day. Hey, if you make anything cool following this tutorial, tag me at Zircon45. I'd love to see what you made with this.